For cycloalkanes, just looking a little bit into a different type of conformational analysis, we did a lot of Newman projections already. And so Newmans are good for acyclic compounds. Cyclic compounds, there is still angle strain. There's some sort of higher energy type of an idea. If the ring was flat, then all the carbon bonds would be eclipsing too, and it would cause considerable torsional strain. What we'll see is that in cycloalkanes, we're not perfectly flat. But what I do want us to remember is the angles here. We know for an sp3 hybridized carbon atom, we should be 109.5. Now think about that three-membered ring. 60 degrees, right? For a perfect triangle. That's a heck of a lot of angle strain, right? We're thinking these carbon bonds want to be 109.5 and we are putting them in 60 degrees. A three-membered ring is highly strained. Same thing with the four-membered ring, 90 degrees. A five-membered ring is a little bit better. If we were perfectly flat, a six-membered ring would be 120. You might not know the seven-membered ring, a 129 bond angle, and the eight-membered ring is a 135. Thank goodness not all of these are flat. These would be if we had a flat ring. We don't have a flat ring, thank goodness. But we can start to see is somewhere in here is that threshold of being stable, right? Letting the sp3 hybridized carbons have their 109.5. In a combustion analysis, this is what was first identified. It identifies that the six-membered ring is actually the lowest energy molecule. We will focus our attention, and I know I said this in the very beginning, it's a hexagon drawing class. The reason why we focus on the six-membered ring is because the heat of combustion per kilojoule or per CH2 group is the smallest kilojoules per mole. That means it is the most stable out of all of the rings. Five-membered ring is not bad, seven-membered ring is okay, but definitely three and four-membered rings are highly reactive. And we'll be able to see this in real-life type of analysis when we say, why does something move to ring expand? Why do we go from a 4 to a 5? Well, because 5s are more stable. There's less strain on the actual angles. So cyclobutane, we're just going to start with the four-membered ring, is 27 kilojoules per mole less stable than cyclohexane per CH2 group, right? And so the angle strain, because of the bonds being around 88 degrees, right there, there's an 88 degrees. Remember, it wants to be 109.5. But it can't be because it's locked in this ring. There is a slight torsional strain because of the adjacent CHs also being kind of eclipsing here. See, like this. It's not a perfect flat, ring, but it is puckered a little bit. We do have cyclopropane here. It is as flat as we really can be for a ring. But notice that the red dots are where the 109.5 would be, right? If you think about the difference between those red positions. So we can see a big strain right there in the cyclopropane as well. Now, what we need from this information is nothing more than they are highly strained. There's angle strain and slight torsional strain, and therefore they can be reactive. Cyclopentane is very similar in energy to cyclohexane. It's only a little bit more energy. There's only a very slight angle strain. The bonds are nearly 109.5, very close. The big reason is because of the torsional strain, that it's a little bit higher in energy. Specifically looking at the eclipsing hydrogens, it makes this envelope type of a shape. We'll build this molecule again, we'll build it in class so that we can see what it looks like, but we'll see that those eclipsing hydrogens cause a little bit of torsional strain, the torsional strain that we were talking about in Newman projections. All right, for cyclohexane this beautiful structure can adopt a variety of conformations, but its chair conformation, these ones down here, is the most stable. We will practice the flip and we'll be able to see the half chair, the twist boat, the boat, everything like that. We'll mainly look at the boat and we'll look at the two chairs. But what we want to be able to look at is the chair conformation itself and be able to draw the chair conformation. Yes, we can draw the skeletal structure or the bond line structure, but in order to actually draw a conformation, right, an analysis of the bond rotation for cyclohexane, we need to be able to draw the chairs. So cyclohexane has no ring strain in the chair conformation, no angle strain, no torsional strain. Everybody is 109.5. And yes, we'll see some eclipsing things, but they are not adjacent to each other. They're at least 1, 2, 3 carbons away. There are other conformations like we saw in the chart just previously, like the boat and the half chair and the twist boat, and those are higher in energy, but we are going to focus on the chair conformation. Again, you can do a Newman projection for this guy. Here's the Newman, but it's not always readily available or readily easy to understand. So we're going to focus on drawing this guy. This is our chair. Why it's called a chair? Well, you can imagine maybe a little person like sitting in a little lounge chair. There's some legs, holding a nice drink with a straw. Maybe it's got an umbrella. Yeah, okay, well, imagine. Use your imagination on that one. Not super sure why it's called a chair. Kind of, maybe if you squint hard, it looks like a chair. Let's practice drawing these chairs, shall we? Okay, drawing the chair. I like to start with 2 slanty lines, slightly slanted to the right. Right? Excellent. 2 parallel lines slanted slightly towards the right and upwards. I'll make the left a mountain. I'll make the right a valley. And then I'll connect the 2. There's my chair. Beautiful. 2 slanty lines, parallel. My mountain and my valley should also be parallel as best as can be, and then connect them. And those 2 lines should be parallel as well. That was a good one. Good job, Lauren. Let's do one more. 2 slanty lines. Try to make them the same length too. Mountain on the left, valley on the right, and connect them. Practice, pause, take a break. What we want to do next after that is put on the hydrogens. Now, when we want to put on the other groups, remember for each, in a cyclohexane skeletal structure, each carbon has 2 hydrogens. And so it's really these that we want to be able to put on as well and analyze the conformations. So if each carbon is a CH2 group, we have to be able to draw 2 more lines on this structure right down here. I'm going to change my color to pink. Anytime you see a puckered up carbon, draw a vertical line upward. If you see a puckered down carbon, draw a line down. Up, down, up, down. These hydrogens are what we call axial hydrogens. They are flagpoles. They are vertical, up and down. Now, also on those, if the carbon is puckered up, it has an axial up position, and then it has an equatorial down. These are going to be around the equator, around the middle. If the carbon is down, puckered down, and has an axial down, its equatorial is up. Notice here, there's your 109.5, right, between the axial and the equatorial. Equatorial down, equatorial up, equatorial down, equatorial up. Let's try that again. Let's bring another one down. If I have a puckered up carbon, axial up, equatorial down, up, down. If I have a puckered down carbon, I have an axial down and an equatorial up. If we think about the ups and downs being related to, are they slightly slanted up or vertical up in terms of an equator around the middle of the actual carbon ring. So notice up doesn't mean axial or down doesn't mean equatorial. Axial and equatorial result in the position of the actual bond. Is it vertical or is it slightly slanted? Axial is vertical, equatorial is slightly slanted. Up means it's on the upper half of the molecule. Down means it's on the lower half of the molecule. Up and down, axial and then equatorial. Down, axial, up, equatorial. Notice that they do shift. That if you have an axial down, it comes with an equatorial up. The next carbon would have an axial up and an equatorial down, opposites. Excellent. Lovely. Now, with drawing the other chair, it's called a chair flip. Let's draw our chair, mountain, valley, connect the two. I'm just going to draw in one carbon's axial and equatorial, and I'm going to highlight them pink and yellow. Now a flip is an equilibrium chair conformation rotation. A cyclic structure does not have free rotation around a sigma bond like we did with our acyclics and Newman projections. But what it does have is a slight rotation. What we start to see is that if we can push this carbon down, what that would become is my actual boat conformation. And then let's just pull this carbon up. And how we draw the other chair is by doing the opposite of what we just did for the original chair. Two slanty lines to the left. Draw a mountain on the right and a valley on the left. And then connect the two. Now where is HA and HE? They've moved down. HA and HE have technically swapped their axial and equatorial nature. That I didn't highlight, rude. This was axial up and equatorial down. When we do a chair flip, we are trying to rotate. We take one carbon and pull it down. We take the opposite carbon and pull it up. Now we are equatorial up and axial down. We'll practice with the flip in class with an actual structure, with an actual molecule kit. What's important, axial changes to equatorial, equatorial changes to axial. Notice the yellow hydrogen was equatorial and now it's axial. What doesn't change is what is down stays down and what was up stays up. The yellow hydrogen was down to begin with and is still down. That cannot change. What was up, the pink hydrogen, stays up. So axial and equatorial flip, but the actual idea of up and down does not. All right, it's easier kind of to see these with a substituent. So we have methyl cyclohexane here. The chair conformation where the methyl group is equatorial is more stable, 95% to 5%. Why? Well, something that we call 1,3 diaxial interactions. The 1,3 diaxial interactions is where these groups already start bumping into each other. There's sterics here. There's the strain of big groups trying to bump into each other. And so just like when we saw steric strain from the gauche position of Newman projections, these are, yes, far away. They're 1, 2, 3 carbons away, but they are still axial. They're eclipsing each other. And so they can bump into each other. That's why in equatorial positions, notice he's actually just perfectly eclipsed. He's not perfectly staggered, staggered in between there. And so what we start to dive into is the idea that eclipsed is bad, and that only happens when big groups are axial. Equatorial is more stable for the big groups. They need more space, so put them on the equator. Larger groups cause that steric or crowding position on the axial. You can see the bigger the group, we go down this list, the bigger the group, the more energy cost it is. You wouldn't need to know these energy costs. Just being able to say and to equate big groups with each other. Notice one that gets mistaken a lot, halogens versus methyl groups. Methyl groups, remember, is a CH3 group. We have a big old CH3 group attached onto our molecule versus a little old chlorine, which is just one atom, right? So be very, very careful with looking at this chart. Halogens are small because they're not bonded to anything else. OHs are a little bit bigger, CH3 groups are bigger, ethyl groups are bigger than that. Then we have the isopropyl group and then the tert-butyl group. The bigger the group that we get, the more strain we have on the actual cyclic structure. And so make sure, end of the day take-home message, big groups we try to put into the equatorial positions if possible. Now, if we have a di-substituted position with wedges and dashes to show positionings, a couple of things to note. A wedge, the CH3 group wedge, that means up. Dash is down. That always is the case. Dash will always equal down. Wedge will always equal up. So when we're drawing our chair and we want to start putting these guys in a specific position, choose 2 carbons, carbon 1, carbon 2, carbon 1, carbon 2. I have to put chlorine up and I have to put methyl down. That doesn't mean I can't do a flip and analyze. Well, what happened? Chlorine is still up. Methyl is still down. I'll do CH3. Me is the same as methyl if we hadn't seen that yet. And now we can analyze with these 2 conformation which one is more stable. Well, this one is stable because the 2 biggest groups are both in equatorial versus both in axial. We will practice di-substituted groups together in class. Just be aware that they could come up. And ups and downs are important for us in these di-substituted cyclohexanes. Just a couple of introductory things. We're going to do next chapter stereoisomerism. We're going to talk about stereoisomers. Now, a stereoisomer is one that the connectivity is the same, but the orientation is different. And so when we're looking at those different orientations, specifically with our six-membered ring, what I want to present here is the idea of when we have two groups and they're on the same side, both up, both down, right? Either one, both up or both down, that is what we call cis for same. And if we see groups that are on opposite sides, one's up and one's down, that is what we would call trans for opposite. So cis and trans are going to be a simplistic way of identifying two groups. If they're both up or both down, we use cis. If one's up and one's down, they're on opposite sides of the six-membered ring structure, then we would say that's trans. Again, this is just a common naming system. We're going to go into it a little bit more in depth later on.